Ladies and gentlemen, welcome to this PlugFest. In comparison to other conferences, you have the pleasure to not need to listen all the talks over 2 days. In the afternoon latest, you will put your own hands on your own notebooks to do coding. But we have the pleasure to do some introductory talks. And well, I'm one of the architects behind AutomationML, and you can easily imagine that it would be easy for me to talk about AutomationML the full day, and I really would need the full day to show you all the bells and whistles and all the beautiful concepts behind AutomationML. While preparing this talk, so I finally found out that I have to focus on the basic principles of the architecture, and I found this picture. And to be honest, this picture, this is a key element of what architecture is. It is showing a building. And this picture shows much about AutomationML, by the way, probably more than one of these technical slides you see afterwards. This building is not just a building, it is somehow an integral part of the ecosystem around. It is integrating the environment with the principle of the building itself. It shows the harmony between the ecosystem around and itself. And this is one of the key elements of AutomationML. It's an integration format that tries to interconnect things that are usually loosely coupled. But we are in a technical world. So we don't erect nice buildings. We make an architecture of a data format. And what we finally would like to reach is we want that computers exchange data. We want computer being able to read and to understand electronic data. This is not about PDF, this is not about Excel sheets, this is not about handmade drawings. This tries to cover syntax and semantics, the content and the meaning of things. And one of the key elements of automation is that we are also able, or that a computer is also able to understand what it is not understanding. We have the possibility to explicitly model the unknown knowledge, one of the core elements. Well, this is what we want to reach finally. And exchanging data between engineering tools in a heterogeneous tool landscape is not easy. It's finally it finally needs the power of a language. We need a language. And that's why it's AutomationML. It's a markup language. And whereas a lot of approaches in the community over the last decades try to reach exactly this, AutomationML tries to go another way, because we found out that there are timeless principles that will survive hundreds of years, that are so basic and so sound that we want to model them explicitly in AutomationML, whereas other concepts are so domain-specific, vendor-specific and time-specific that we do not want to model them directly as part of the data model. So, and to come to the basic principles, finally, we need to find the timeless elements every plant finally has. You see here a simplified structure of an industrial plant, with some PLCs and robots and HMIs, communication hubs and so on. And what are the basic principles? The basic principles are that you have elements in it. You have objects inside of it, objects that you can order. This might be physical objects, but this also might be logical objects. You have interfaces. These objects need interfaces to interconnect with each other. And because it makes sense in industry to reuse components that have already been proven and being part of a product offering, for instance, we know compositions. Compositions as modules, as units, as subunits, whatever term you want to use here, we name it here, compositions. And the fourth timeless concept behind AutomationML is the modeling of hierarchies. Hierarchies are a beautiful way to structure data. And we will have hierarchies in 100 years, and we will have them across all competitors, across all continents, across all political ecosystems, because they are a generic concept. That's why they are natively embedded into the AutomationML. And finally, to be able to model planned data, the first concept is we want to store the topology of a plant. This means mainly an object model with hierarchies, with objects inside. And for this, we decided to not develop our own data format, and we finally decided to not develop any data format by ourselves. We want to make use of existing and established data formats that already comprise the intellectual property of many years and many intelligent people. And for the topology, we decided to go for the IC 62424, which is the CAX standard. This is so generic, you can model every type of hierarchy, every type of data model with that. It is not bound to manufacturing plants, it is not bound to process plants. It is, you can model your family tree with that, and the structure of the toys you have for your kids. So this is available. We use it for plants, for cells, and it contains concepts for components, attributes, interfaces, relations, and references. So for us, for the automation engineers, this is really object-oriented. But on the other hand, things have a shape. Objects have a shape, they have a geometric appearance. And so we looked for what kind of data format could be helpful to model geometry, and there are lots of candidates around, and you know, that we finally decided to go for Koyada, the language that is behind Google Maps, Google Earth, that is behind Sony, that is behind PlayStation. This comes from the gaming industry and is extremely powerful, and yeah, it contains geometry and kinematics, and from my knowledge it is the only free file format that combines both. The next subformat is PLC OpenXML. We tried to model behavior. Behavior is an extremely important thing if we come to automation data. And yes, that's so. We found PLC OpenXML very useful, and we have embedded it into our architecture. From the concept, we are able to address more future XML standard formats for different aspects we possibly don't even know today. So we have key elements to address the embedding of further data models. So, and this is now AutomationML. AutomationML is not equivalent to CAX. It's not equivalent to Koyada, to PLC OpenXML. It is the glue around. That's why AutomationML is very small. If you just look into the architecture part of the AutomationML standard, you will find out that the normative part is about 35 pages. Compared to other standards, this is really small. And this is because we just reuse things and we interconnect them together. So, the glue of AutomationML means that we are able to make a reference from an object in the CAX document to a Koyada file. For instance, here for this robot. Or we are able to model the logic that should run on the working cell here by making a reference to a PLC OpenXML file. And this can also be done for a single signal. We can point to a certain signal within the PLC OpenXML document. This allows us to interconnect signals on the CX side and to reference them into different PLC OpenXML documents. So, and this is why our standard architecture has certain steps and certain parts. Part one of the AutomationML standard is only about the architecture. It explains these basic principles of how the AutomationML world combines different data formats. The second part then is about semantics. It's about libraries, role libraries. Part 3 is about geometry and kinematics, and part 4 is about logic. And so we have a series of standards expecting that further parts will come later. Well, then I thought about how can I explain the technical architecture of AutomationML. I can show you some XML snippets. Many of you will be computer science scientists and are very familiar to read this. Others may be more in favor with these trees we know from XML Spy, but I try a more simple approach, because there is a beautiful symmetry in AutomationML, in this object model around CAX. And this means that you mainly have an instance hierarchy. This is your project. This is the root element of where you store the data you want to exchange. And this instance hierarchy can just contain internal elements, and these internal elements have no meaning, and they are just placeholders for the data you need. And internal elements can contain internal elements and can contain internal elements, and you will find internal elements all the way. And this is the main principle here, and this is close to be everything. This is still meaningless. It's a meaningless hierarchy of internal elements with no further meaning and content. So, and internal elements can have interfaces. This allows us to describe connection between these bubbles, but still, even these interfaces have no further meaning. To give them a meaning, we have two different concepts here. We have the system unit class library. This allows me, for instance, as a member of ABB, to model the component RB6000, which is a robot of ABB, with all the details, with all the geometries, attribute parameters, requirements, whatever is characteristically important for this robot. So, and then I can make an instance of this in the instance hierarchy, and then I get content. But there is another concept. There is a role class library. The role class library contains objects with the standardized semantics. It, for instance, just contains the class robot, and this is a generic class, vendor independent, and the meaning of this can be standardized. That's why we have the part 2 of our standard giving you libraries of objects. But they are vendor independent, whereas the system unit class library might conclude a component catalog which is vendor specific and very proprietary. So, and this is, by the way, this is a huge difference between the object-oriented paradigm in the computer science and what we need here in the automation world. Because whenever you want to model something in the computer science world, in the IT world, in the software informatics world, you make a class and then you instantiate the class and that's it. We do it differently. We start with the roles. We can associate roles, generic roles, to proprietary components to give them a meaning, to give them the computational interpretability. And then we can instantiate them. But you can also just make a reference between the placeholder and this role class to give your internal element a meaning. And then you can describe your requirements. Here I need a robot with this and that requirement. And finally you make a selection, and then you associate them to the ABB robot or to the KUKA robot or to whatever robot you need. These are very important concepts that you do not find in the object-oriented paradigm of software development. And this is really helpful, and I know this is not this does not follow the object-oriented paradigm that we know from the computer science, but having this makes it really applicable for us. And not having this is maybe one of the reasons why object orientation took so many years to be adopted in the automation world. So, hierarchies. We can store hierarchies in CAX exactly in the same way as we would depict them in a graphical way. They are stored hierarchically. And this is very symmetric. The internal elements contain internal elements. You can see this very easily. This is a typical project structure. Here you have a location structure, a bus topology, a hardware structure, 3 different structures describing the same plant, and they might be interconnected. This is one of the things you will finally develop when you develop automation exporters and importers. In the first part of our standard we have a couple of libraries. The left one is our role library. These are the key roles that we always need. Everything is resource. Everything is you can with 6 or 7 of these roles, you can really describe a complete plant already on a rough semantic basis, of course. You have structures, process structures, resource structures, you have facets and groups. These are concepts you can find in our architecture that really have a deeper meaning. And we have a couple of standard interfaces on the right-hand side. You see the possibility to connect Koyada files here. There are standard interfaces that give you the possibility to store the URI or the file path to a certain Koyada or PLC OpenXML file, for instance. And finally, I want to give you some feedback from industry about the applicability of AutomationML. In the last year, we founded the GMA-Fachausschuss 6.16, which is a combination of 19 organizations, and they want to exchange data via AutomationML in the process industry. This is not related to manufacturing industry. And they developed AutomationML exporters and importers. And the first feedback came from Rösberg. Here we sat together with the development head, with the facility head, and with my person in one room. And they had no starting experience with AutomationML. And within 4 hours, we developed the AutomationML exporter. 4 hours. And he finally concluded and officially stated here, the facility manager, that even in the code, you mainly don't see the AutomationML because most of your code will fight with the C interfaces to your engineering tool. Grabbing data out of the engineering tool, this will be 90% of your code. Storing them in AutomationML is simple. With Alcotech, we did exactly the same story again. In the second meeting, I sat together with a very smart developer from Alcotech, and we needed 4 hours to develop an exporter and an importer. And he finally finished with the words, "This was not a challenge, I'm disappointed." And ASPlan, the CEO of ASPlan, reported me later, and he did it by himself, alone, without any support from me or one of the automation community. He came, and in one of the last of the next sessions, he came to me and said, "Hey, Rainer, I want to complain. Your promise to be able to make it in one day is really not realistic. We are disappointed. We took 2 days." I think this is quite an impressive message. Whenever you work with AutomationML, you will find out that it is in the end not that complicated, and the most complication will come from your engineering tools, because they are probably not so open as they usually promise. And about the openness of engineering tools, we will have in a second session. Thank you very much. To summarize what you have heard, the key elements of the AutomationML architecture is the reuse of established data formats. We have a strict separation of syntax and semantics, which allows us to agree on something. If you look on other standards where they try to combine syntax and semantic in the meaning of let's model every item that we know in industry, every signal, every device, everything, they do not finish. And in the end, they produce thousands of pages that finally nobody can understand afterwards. That's why it is small, it's extensible, you can adapt, you can add semantics libraries later on. You will see that during the day. And one of the economic success factors of AutomationML is that it is industrial driven. It was not an idea of somebody in the sky. It is driven by Daimler, it is driven by ABB, it is driven by Siemens, it is driven by others. We have heard about the number of organizations behind it. Second, we have software. You can use free software to access AutomationML. You can store an AutomationML file with a single line of code. You can open an CX file with a single line of code. Elko van der Waal, the head of the PLC OpenXML community, finally said, "Oh, crap, we should have done this in the beginning of PLC OpenXML also, then we would have more success." Yeah, this is really helpful, and it's free. It's free. There is no charge for using the standard compared to E-class, where you have economic boundaries here. This is really one of the benefits. Thank you very much. Any questions?